Hello, my name is Saurabh. Today I'll be presenting an overview of infrared thermography, in short referred to as IRT. Now, IRT has become a powerful non-contact method for observing temperature distributions at the surface of any body. It has a wide range of applications in engineering diagnostics, structural health monitoring, and even in medical imaging. Now, I'll start with a brief introduction and historical background. Then I will explain the conceptual and optical principles behind how infrared cameras work. After that, I will discuss a typical experimental setup used in IoT systems. We'll then look at two important applications categories, passive and active thermography. Finally, I will summarize the key limitations and conclude with the main takeaways from them. Infrared thermography is a non-contact optical method that converts invisible infrared radiation into visible thermal images. Any object with a temperature above absolute zero emits infrared radiation, and by capturing this radiation, an IR camera can map temperature variations across the surface. Here you can see there is an image of a laser reducer. The concept of infrared radiation by Sir William Herschel's experiment in early 19th century provided the layout of this IRT. Early infrared devices were primarily used in the military, especially during World War II for aircraft imaging. Over time, the technology improved tremendously, and today, IR cameras have become compact, portable, and highly sensitive, making them valuable tools in modern diagnostics and inspections. Now, infrared thermography is basically based on the principle that any object above absolute zero temperature emits thermal radiation. According to the Stefan-Boltzmann law, here we can see the emissive power increases rapidly with temperature is in the fourth order. Infrared radiation spans wavelengths from 700 nanometer to around 1 millimeter, making it invisible to the naked eye. But IR sensors detect this radiation and convert it into electrical signals, which are digitized into thermal images that reveal surface temperature variations. And the image shown here is a regular photograph, and also there is a thermal image attached to it. It's the image of a Faculty of Engineering in Naples. The thermal image highlights the temperature differences across the building facade. This helps to find the material contrast that are invisible in naked eye in standard photo. Now let me explain the optical principles behind an infrared camera. The thermal radiation emitted by the object is first focused by focusing optical lenses. Unlike visible light cameras, IR cameras use materials like germanium, zinc selenide, or silicon because these materials transmit infrared wavelengths effectively. The focused radiation is then directed onto an array of infrared detectors. These detectors, which are usually made up from materials like indium antimonide or mercury cadmium telluride, they convert the incoming radiation into electrical signals. As these signals are extremely weak in millivolts, they need to be amplified and also digitized. The camera then processes this data into a two-dimensional grid, forming a thermal image. The resolution can vary from low-end arrays like 120 by 90 pixels to advanced systems reaching 1280 by 1024 pixels. And of course, calibration is essential because emissivity and environmental conditions can significantly affect the measured radiative power. Now, this is a typical experimental setup for IRT, especially in research or high precision applications. It includes several additional components beyond the camera itself. A light source such as a monochromator or pulse theta may be used for active thermography. Optical elements like focusing lenses and mirrors help direct radiation precisely toward the detector. The sample is often mounted on a rotary stage, allowing the system to capture different views for three-dimensional reconstruction. In some steps, the system captures both emission and transmitter signals to analyze internal features. Because the thermal events occur quickly, the IR cameras used here often have very high shutter speeds and excellent temporal resolution. For example, FLIR's SC7000 series is a very common example in these kind of setups. Now let's talk about some applications. Passive thermography is the simplest and most widely used approach. In this method, the system relies purely on the natural thermal radiation of the object, meaning no external heat source is needed. This makes passive thermography ideal for applications where the structure is already operating under thermal load. For example, here you can see the IR images of a building in day and night condition. Also, electrical equipment such as transformers or circuit panels, they naturally develop hotspots due to faulty components. Similarly, building diagnostics often rely on passive imaging to detect insulation failure or air leakage. And of course, in these cases, the objective is to simply locate thermal anomalies. Talking about active thermography, on the other hand, involves applying a controlled heat pulse to the surface. After the surface is heated, an infrared camera monitors the cooling behavior over time. Defects such as voids, delamination, or cracks affect the heat diffusion process. This causes detectable temperature differences on the surface. It's an extremely powerful tool in non-destructive testing of composites, building materials, and aerospace components. Here comes the interesting part. Active methods allow us to reveal features that are hidden beneath the surface, unlike passive thermography. Now, although infrared thermography is a visible diagnostic tool, it does come with important limitations. First, it is primarily a surface-based technique. Thermal diffusion limits how deep we can detect features, typically up to a few millimeters. In addition, accuracy depends heavily on surface emissivity. Highly reflective or metallic surfaces can distort measurements and often require spatial coatings or calibration. Also, the technique is very sensitive to environmental conditions such as wind, humidity, and ambient temperature, all of which can influence thermal mapping. So, careful setup and better interpretation are essential for obtaining reliable results. To conclude, infrared thermography can be called as a versatile, non-contact, and non-destructive technique that converts emitted infrared radiation into meaningful thermal images. Its effectiveness depends on the camera's optical components, detector sensitivity, and proper calibration. Passive and active thermography each offer unique advantages depending on the application, while the technique is limited mainly to surface analysis and sensitive to environmental conditions. However, its portability, cheapness, and quick setup makes it widely valuable in engineering diagnostics, structural inspection, and medical applications. Overall, infrared thermography continues to be an important tool in modern diagnostic technology. Here are the references. Thank you.